All right, welcome back. In this video, we're moving past our previous hypothesis test and on to analysis of variance, otherwise known as ANOVA. And we'll start out with this one way between subjects analysis of variance. And so to orient us a little bit, remind us where we're at in the course. So previously we looked at z-test and a variety of t-tests. And you'll notice here the primary difference between what we're doing this week, ANOVA, what we've done in previous weeks, is our number of groups. All right, at this point we're still testing for differences between groups with one factor, but now we're looking at more than two groups, and that brings us to ANOVA. And we'll start with between subjects observations. So in terms of what ANOVA is, I guess to back up and talk about why we're moving past t-tests. So like I just stated, I guess to elaborate in a bit more detail, t-tests are always going to be limited to testing differences in one or two groups, right? And so if we talk about groups in terms of k, that means k is one or two. But in reality, right, in the quote unquote real world, we'll often test hypotheses that involve more than two groups. So for a variety of examples, say we're developing some experimental drug, right? Like, yeah, whatever it may be. I've heard of someone on my campus right now developing a new antidepressant drug. Antidepressant drug. Wow, not a drug. An antidepressant drug, and the only way to verify that that works is to do a drug trial, right? And so you might have a control group who gets like a sugar pill or something like that. Then you might have different dosages to try to dial in an effective dose, right? So there might be a control group and then people getting increments of 10 milligrams, like in this example. Say we're developing some new training program or maybe a new learning condition, right? Like ever since this was happening before COVID, but ever since COVID, there's been a surge in a variety of teaching modalities, such as in person, online, some sort of hybrid or high flex, right? There are all these different terms. So maybe we want to test these to see if one is better than others, right? And so we might have a variety of different conditions rather than just comparing two specific conditions. Maybe in a more clinical or counseling context, if we're doing different therapy modalities. So it could be people who are being studied, people who get treatment as usual, people who get CBT, cognitive behavioral therapy, right? There are just a few examples here. You can probably think of more examples in the context of whatever it is you study in social science. But point is, there's a lot of times when we can't just look at two groups. And in those instances, ANOVA, or an analysis of variance, can be helpful, right? And so here we're looking at one or more factors with the variance of two or more group means. That's what we're focused on. Variance in one or more populations is unknown. And broadly speaking, this is also called the F test because we're looking at the F statistic. And before we go further into ANOVA, I want to pause and deliver a promise from long ago and to actually talk about what factors are. So let's talk about what a factor is in this context. And really, because there's lots of, I'd say, contexts out there in which you might use this term or hear this term. But in the context of the statistics in this specific class, factors are variables that may have an effect on the dependent variable. And it may help to think of it this way, right? I'll give you an analogy here. So you can think of if we're thinking about some particular relationship we're trying to study, some event, some effect, some decision, right? Whatever it may be, we might ask, what are some things that might factor into that? And so let's go with a very practical example to try to identify what I mean by this. So let's say, for example, currently the time I'm recording this, it's springtime. Summer's not quite here, but it's on the way. And so we might think, okay, let's go camping, right? Let's get outside. And if we ask this question, should we go camping this weekend, right? Say you come home, talk to your partner, roommate, buddy, whoever it may be. You're just like, what do you think? Should we go camping this weekend? Well, ultimately, when you're making that decision, you're ultimately deciding if you're going to enjoy the experience, right? Is it worth our while to go camping? And so we can call that our dependent variable, right? Camping enjoyment. Am I going to be happy doing this? And so let's assume that you enjoy camping for the sake of this example. And so this is something you'd want to do, but there's probably going to be some other things that factor into that decision. right? It's not every single weekend that you're going to go camping simply because there are other things that factor in. For example, the weather might play a role, right? Like if it's going to be sunny or rainy or snowy. So weather, what time of year it is. Broadly speaking, what's the forecast look like, right? Are we going to be stuck inside a tent where we can't do anything? Are we going to be freezing to death, right? So that might be one factor, the weather. And we might also ask, do we have the right gear and supplies, right? If you want to go camping, but you have absolutely no means to, that could probably factor into that decision, right? So do we have the right gear, the supplies? Do we need to buy anything? Do we need firewood, right? Whatever it may be. Availability, right? So like, are there camp spots available, or do we know of good backcountry dispersed sites that we can go to where we don't need reservations or don't have to pay a fee? Do we have other plans? Are we available, right, beyond the campsites? Are we available to do this? Will we be bailing on someone that we already made a promise to, right? So just some examples of the fact that when we ask ourselves these questions and we're making these decisions, we're sort of weighing these different variables and we're accounting for things that factor into our decision. And so we can literally use this as an example of factors in like a hypothetical ANOVA or something like that. This would be a weird one to have any sort of measures for, but hypothetically, if this was an ANOVA and camping enjoyment was our dependent variable, these are some examples of factors or independent variables that might affect that dependent variable, such as the weather, our preparedness, our availability, right? A basic example, but hopefully this helps to explain a little bit more of what we mean when we talk about factors and statistics in this class. And so we're going back to an ANOVA to use a more practical example, or I don't know if more practical actually is an accurate thing to say, a more, topical example, I guess, for ANOVA. So imagine we want to test how price affects food purchases, right? Are we more inclined to buy stuff if it's cheap or expensive, and does the healthiness of that food play a role in that too? So let's say we're doing some study and we have a buffet here, and half of the buffet is unhealthy food, right? Junk food, donuts, pizza, right? Just crap, right? Stuff that's fun to eat, but will be detrimental to your health if you consume it every single day of your life. And then half the buffet is healthy, right? Foods that are generally nutritious, generally good for you, generally good for your body, your digestion, so on and so forth. And so we look at these different groups. And so let's say in one condition, this pricey group, we have them come up to this buffet and they can choose different foods, but healthy foods are expensive, so they'll have to pay more. And so we're seeing if they're willing to do this. Whereas the cheap group doesn't have that problem, right? Healthy foods are cheap. So we want to see how these two groups are buying various foods, depending on whether the healthy food is expensive or cheap, right? And so we do this and we record the total calories chosen. And let's say our hypothesis is that participants in the cheap group will choose a lower calorie meal simply because those healthy foods are more affordable, right? So we're kind of assuming that most people want to eat healthy if they can afford to. But so far, if you've been paying attention, you're thinking about what you've learned in this class so far, you'll note that this is an example of a two independent sample t-test, right? At this point, k is still just 2. And so let's ask then, okay, what if we added a control group, right? A control group in which all prices are the same, right? There is absolutely no difference between unhealthy and healthy food, right? And so I guess we should say here, in the pricey and cheap group, healthy foods are more expensive than unhealthy. And in the cheap group, healthy foods are cheaper than unhealthy, right? And then we have a control group where everything's the same. And so we see if, okay, in this case, if people choose healthier food, then we could assume that, okay, people do want to eat healthy, even when prices are the same. Whereas if it's one of these two groups, we might say, okay, people buy food just solely based off the price, right? So we can kind of have a variety of outcomes here. But now, since we have more than two groups, we need a new way of testing this in order to tell where the significant differences are, right? Because we're doing more than just this comparison between two groups, right? Here we're comparing this group and this group, this group and this group, and this group and this group, right? So there's 3 comparisons ultimately that we're making here. And so that's why we'll use an ANOVA. And there are different types that we'll go through in the next few units in this course. And ultimately, the type depends on a few things. One is the number of factors being tested. right, which we just defined factor. And the number of factors being tested is clearly stated in the name of the ANOVA. Like here we're doing a one-way ANOVA in this module, so that's a one-factor ANOVA. Two-way ANOVA is a two-factor ANOVA, and so on, right? If I said a four-way ANOVA, that means there's four factors. It sounds complicated, but ultimately that's what that number means in the title of the ANOVA or the analysis. And we'll also make this decision based off how participants are observed, right? So within subjects, yeah, previous slide example, same sample, different measurements, right? So we're looking at measurements in the dependent variable within the same people or between subjects. So yeah, again, now we're looking at independent samples, something we defined previously, so I won't elaborate on further here. Yeah, and so what we're doing this week, we're starting out with the most basic type of ANOVA. And so in this test, different participants are observed at each level of the factor, right? So the between subjects refers to the fact that we're doing independent samples, right? Different participants. We're looking for a between subjects effect. And one way, again, indicates that this is a one-factor ANOVA, right? There can be multiple levels in that factor, but only one factor nonetheless. Okay, and a few things to note before we go further. Notation here is slightly different. So here, little n refers to the number of participants per group, and the number of groups is indicated by k. And then big N, capital N here, is the number of total participants, right? So for example, if we had a drug trial in which 10 people get placebo, 10 get 10 milligrams, and 10 get 20 milligrams, then K is going to be 3 because we have a control, 10 milligram and 20 milligram. Our overall N is going to be 30, right? 10 plus 10 plus 10. And then our little n is 10 because there are 10 per group. And so in other words, to calculate big N, we can multiply K times N, right? 3 times 10 yields 30. That's our total sample size. Okay. Wow. Okay. Some other key terms, source of variation. So this is any variation that can be measured in a study. This will vary depending on the type of ANOVA we're doing. The goal here isn't to complicate things or to confuse you, but just to note this because these are terms we'll come back to as we're talking about different pieces of the analysis. And so in a one way between subjects ANOVA, the two primary sources of variation are between groups, right? And so in this example here, if we have 3 classes and we're comparing means between the classes, like psychology, sociology, biology, I don't know, maybe this is some measure of difficulty or something. Then between groups is comparing the means, right? Because that's the best way to compare the groups, right? We have a mean for this group, a mean for this group, and a mean for this group. We compare those and we can see the between groups variation or variability. Within groups variation, or in this context, we call it error variation, is variation attributed to error. And this is where it gets a little bit confusing. Here we call it error in this test because it's essentially its variance outside of the mean. And we're comparing just like that specific piece of the group in our between groups variation. And so in this context, any variation within the group is considered to be error. That if that's confusing, I wouldn't. Yeah, my advice would be to not focus on the why and instead just focus on the what, which is or the how, I guess, which is how we'll analyze it. And in this context, just note that if we talk about error variation, we're referring to within groups variation, right? So those are the two primary sources of variation in this test. And now, since we're doing an F statistic or an F test, we'll be using a new distribution, the F distribution, which looks like this. You can see it's very positively skewed. So highest probabilities of getting a low value. And then the larger our F value is, ultimately, the lower the probability is of achieving that statistic. Yeah, we can just kind of leave it at that. Yeah, and so here you can see alpha. So when we set an alpha level, ultimately we're setting where in this x-axis this value falls, right? Okay, the test statistic. Yeah, I guess we'll start with the equation work backwards. F obtained, and our F statistic, is a simple division Ultimately, what we're doing here is we're testing. We talked about the two sources of variation. We're kind of testing those two variations. So here we're looking at the variance between groups divided by the variance within groups, right? That's because ultimately we're kind of trying to like parcel out the variance between groups, right? And so if our value is more than 1, then that means there is more variation between groups than variation within groups. Whereas if our value is less than 1, like 0.26, that means that there is a stronger or a larger denominator, right? So in other words, there's more variance within groups than between groups. So it's suggesting that there really isn't meaningful group differences. So it's a very basic thing right off the bat, is that an F statistic greater than 1 means that there is more variance between groups than within groups. And so the way we'll actually assess that mathematically is by analyzing mean squares. And so ultimately that's a measure of variance. And so we'll have mean square between groups and mean square error. And again, here error means within groups. And so we'll talk more about mean square. If that might be a new term to some of you, we'll get there. Or I guess if you go back to when we talked about variance, it might ring a bell there. But okay, so degrees of freedom, some more foundations before we go into our example. So in this test, total degrees of freedom is the same as it has been, n minus 1, this context, big N, right? Because that's for the overall test, the total sample. But we will split this into two parts. One measure of degrees of freedom for each source of variance. So ultimately we'll have a degrees of freedom between groups and a degrees of freedom within groups. And so different terms you could use for this, dfbg, dfnum for numerator. Ultimately here we're talking about degrees of freedom for the numerator, right, in our calculation of the F statistic. And ultimately here, that number is simply k minus 1. So the number of groups minus 1. That is the degrees of freedom for the between groups portion of our analysis. And here DFE, again, DF within groups, DF denominator, however you want to refer to it. Here that is simply n minus k, right? So the total sample size minus the number of groups. All right, and so to give you a visual for that, if ultimately what we're doing is comparing variance between groups to variance within groups, these are the degrees of freedom that we'll consider there. And so you'll notice here at the top, we're referring to variance between groups. We're only interested in the number of groups. We're only looking at that in our calculation of degrees of freedom. And variance within groups, we're looking at across all participants minus the number of groups. That's how we're calculating those degrees of freedom. And so when we report F statistics, we report these two degrees of freedom, right, between groups and within groups. And we always state DFBG first. So for example, if we did an analysis, just like what we talked about previously in one of the previous slides. So say we had a one-factor analysis with 3 levels. So we're looking at type of class and the 3 levels for psychology, sociology, and biology. And there are 5 students per class. Then in that example, our K is going to be 3, because there's 3 levels or 3 groups. Little n is 5, because there's 5 students per class. And big N is 15, because 3 times 5 is 15, and that's our total number of participants. So then we can just calculate each of those types of degrees of freedom. So total degrees of freedom is 14. Between groups, k minus 1, it's going to be 2. Right, we're just pulling our numbers from up here. And for the denominator or error, it's going to be 15 minus 3 is going to be 12. So then we say 2 and 12 degrees of freedom. And when we report this in our write-up afterward, we'll say F parentheses 2 comma 12 close parentheses. Right, so now we don't just report 1 degrees of freedom value, we report 2. Yeah, so pretty basic stuff, but wanted to go over it in advance. Okay, we're almost at our example, so hang in there. Our hypotheses now are slightly different than before. Now our hypotheses are essentially statements about variance. Sigma squared, you'll recall, is a measure of variance or a notation of variance. And so now we're saying the variance of group means, right? Mu or sigma sub mu squared so equals 0. Then we're saying that the variance of group means is 0 in our null hypothesis. So in other words, we're saying that there is no difference between group means. Ultimately, that's what we're saying here. And then if we're saying that that number is greater than 0 in our alternative, then we're just saying that the variance between groups is greater than 0, or it is positive. So in other words, there is variance between group means. So that's basically what our hypotheses are saying. No variance between group means, yes variance between group means. Right, that's just our way of notating it. And importantly in this test, our sample size, sample size for each group, so little n, must be equal in each group, right? A basic assumption here. Other assumptions that I should go into, but again, I'm not going to in this class, or at least, yeah, for the sake of not making these videos even longer than they already are. So let's look at this example 12.1 here. So let's say that we're part of some research team and we're examining employee turnover rates. Turnover is essentially the rate at which people leave a job. So if there's a lot of turnover, it means people aren't sticking around. They're getting hired and then leaving. And so we're looking at those rates of turnover. And we conduct a study in which we're working with this company and they have a bunch of new employees. And we ask those new employees how long they expect that they'll stay at the company, in months, for example. And so employees are assigned to groups, as we're doing this, we also ask them questions about how stressful they think the workplace is. And then we assign them into groups based off what they report. So if 10 say it's highly stressful, then we group them as high stress. 10 said it was moderately stressful, so we group them as moderately stressed. And 10 rated it as low stress. And then we ask them, like we said, how long they would stay at the company in months. Or maybe this is years. We'll just say it's months. And the responses are recorded at the right. So you can see people who are rated as low stress, moderate stress, and high stress. You can see here the n for each group is 10. So then our total sample size is 30. We have k equal 3 or 3 groups. And we want to conduct an ANOVA to analyze significance of the, an ANOVA at alpha 0.05. Okay, so let's do it. Our steps are going to be the same as before, right? So that's familiar at least. So first, let's state the null and alternative hypotheses. Exactly what we just showed you before, right? There is variance between group means and there is not. I said that backwards. There is not variance between group means and there is variance between group means. All right, so that's simple. Set our criteria. We already know alpha is 0.05. We calculate our 2 degrees of freedom, k minus 1 and n minus k. Then we look these up in our table in the back of the book, the F table. If you need help with that, let me know. Again, I'm trying to move a little more quickly through these portions of the videos at this point in the semester at least. So here F grade equals 3.35 based off our alpha and our degrees of freedom. So next we're going to compute this test statistic. This is a simple formula. However, to obtain these two values, we have some work to do. And so, I hate to say it, but there are a lot of steps at this point. Specifically, we have 4 steps in order to finish this analysis. Preliminary calculations, intermediate calculations, sums of squares, and then completing the F table. So let's just walk through those one by one. And so let's go back to our table with all the data here. And to do we're still in step 3 through all this, but we're in stage 1 of step 3. We're going to do preliminary calculations. First, find k and n. We've already done that, but let's refresh our memory. K equals 3, right, because there's 3 groups. Little n is 10, and so therefore we know big N is 30. Okay, now we're going to find the sum of x and the sum of xt. What do I mean by that? Okay, so the sum of x essentially means the sum of these values, right? The actual observed data in each group. So here we're just summing these up. We'd add 3.4 plus 3.2 plus 3.0, on and on and on. And then we'll get that for each of these groups. Right, so we'll have 34.3, 33, and 29.8. All right, so we've done that. And then the sum of x total is essentially just adding up those 3. Right, so sigma x1, sigma x2, and sigma x3 at 34.3 to 33 to 29.8, and we'll get this value. Now we're going to calculate squares, or the sum of squares, essentially, right? And so now it's important to note, this is one mistake that a lot of people make, is that a lot of people assume that sigma x squared is just this value squared. So like for the low group, some people think that sigma x squared, we just square 34.3, and that is incorrect. That's not what we're doing. Sigma means sum of, and here it's the sum of x squared. So it means we're summing the actual observed values squared, right? Or the squares of the actual observed values. It's a better way to say that. So we need to actually square each individual one of these. So 3.4 squared is 11.56. 3.2 squared is 10.24. On and on and on. And then once we have all those values, we'll add those up. And that is what sigma x squared is. Right, so here if we add up everything in this column, we'll get 119.07. We'll repeat that for the next two. And then we'll get our total right there. All right, so again, an important distinction to make is that this bottom row, the squares, is not just the square of this value, right? Rather, it's the square, or it's the sum of all of the individual squares of the observed values. All right. I'm repeating myself, but that's because this is a mistake that I think a lot of people make, myself included, when I first learned this. Okay, that's stage one. Now let's do our intermediate calculations. First, compute a correction factor by squaring the grand total and dividing by the total sample size. So we'll go to, the grand total, sigma xt, we'll square that. So now we are going to square the individual value, because we're going to square this value. And then we're going to divide it by n, and we'll get this value. And so basically on these slides, actually, I'm not going to go through all the nitty-gritty because I'm just explaining what you can read. But basically, pay close attention to the specific instructions and the specific statistics provided in these slides. That's the best advice I can give you as you go through this portion. So step 2 here, divide the sum of squared scores in each group by the sample size of each group. So you can see that here. And again, note that here we're taking these values here, right? Pay close attention. Rather than, actually, I'm going to stop repeating myself because I think I'm just going to confuse you by trying to put words to it. So yeah, just pay close attention to the slides. Then we'll restate the sum of squared scores, yada yada. Now we'll compute the sum of squares. So basically, everything we do in stage 2 on this slide is going to lead into what we do on the next slide. And so for calculating sum of squares between groups, we'll basically subtract our second calculation on the previous slide and the first calculation on the previous slide. And so we'll plug in those numbers here. And then we'll repeat that for these next ones. Again, I'm not going to spend a bunch of time pulling out those numbers because you can do that yourself. I guess for the third one, we'll subtract what we calculated here, SST and SSBG, right? So that's where those values come from. And then we'll use this to calculate and complete our F table. And so sum of squares between groups from stage 3, guess what? That's what we calculated up here, 1.07. Within groups in total, also from stage 3. Degrees of freedom we've already calculated. And so now the mean squares, we're essentially just taking this cell divided by this cell to calculate this cell. And then same for mean square error. We'll take this cell divided by this cell to get this cell. And then our F statistic is this cell divided by this cell. If you're not watching the video, I probably just confused the absolute hell out of you. So here's our values. So you can see them all here. So again, these are coming from the previous slide, degrees of freedom we previously calculated, but I calculated again here for you. And then mean square between groups is simply 1.07 divided by 2 equals that. Same thing for mean square error. and then we'll divide the two to get our F statistic. And so I just moved the table up here, give us some room. Now we need to make a decision. So we'll compare the obtained value to the critical value. Our critical value, if you recall, was 3.35. Our obtained value of 3.52 is greater than that, so therefore it falls in the rejection region, and we decide to reject the null hypothesis. In other words, there is variance between groups here, right? That we're accepting our alternative hypothesis. Okay, and so I know that's probably a lot to take in. However, the fun doesn't stop here. A few other things I'd like to note when it comes to ANOVAs is we also need to do something called post hoc tests or post hoc comparisons. Post hoc is a Latin expression which means after this or after the event. And so basically here, a significant ANOVA is just telling us that there's a significant overall test. In other words, there's some significant difference in all the comparisons that are being analyzed. However, post hoc tests are necessary to actually hone in on and identify the specific comparisons that are significantly different, right? Because again, now that we have more than two groups, there are multiple comparisons going into each test. And so the post hoc comparisons are going to help us identify which of those specific comparisons are significantly different. Yeah, so in other words, these are necessary when k is greater than 2 because we need multiple comparisons. And so here's a flow chart if you'd like some help. Basically, if we have a non-significant ANOVA and we retain the null, we can stop because there's no significant difference to identify. If we have a significant ANOVA and reject the null, then we need to conduct post hoc tests. Okay, and so this is, yeah, this video is getting long, so I apologize. I hope you're still with me. We'll skip that explanation for the sake of keeping it simple. Basically, the point of this slide, there's a variety of tests we can choose from. We'll tend to stick to Tukey's because it has, of the tests with greater power, it is the most conservative. So it's kind of the best of both worlds in that it doesn't have too little power, but it has enough power and it's still conservative among the ones that have enough power. So in other words, it has enough to tell us that there's something there, but it's not so liberal that it will give us a bunch of false positives or something like that. And so to compute each post hoc test, there's basically 3 steps. We'll just walk through these, but these have to do with the group means. So first, let's go back and calculate those in case we haven't already. So in other words, we'll just calculate the means from our values on the table. And so we'll get a mean of 3.43 for low, 3.3 for moderate, 2.98 for high. And then we'll use those in the first step, which is to compute a test statistic for each pair of group means. And here we're literally just subtracting the means from one another, right? So comparison 1, low stress and high stress. The mean for low stress is here, the mean for high stress is here. So we'll subtract the two and get that value. And then we'll repeat that for our other comparisons, right? So here we're literally just subtracting means from one another to get a value that we'll use in this post hoc comparison. Step 2 is to compute the critical value for each. This I'm not going to require you to do by hand. You're going to be able to do this in your stats software. So we don't need to worry about looking this value up or whatnot for now. And then step 3, we'll make a decision to retain or reject the null hypothesis for each. Here we calculated that square root should stop here. It should be equals just 0.43. So that's the critical value. And so basically we'll compare the difference, the mean differences, we'll compare that to our critical value. And if our mean difference is greater than the critical value, we can say we have a significant mean difference. And so in other words, here, if we do this, we'll see that we have a significant difference between the low stress and high stress group, but the other comparisons are not significant. So in other words, our overall conclusion is that we have a significant F-test, and we can say that employees are willing to stay longer if they perceive the work environment to be low stress compared to those who perceive it to be high stress. That's ultimately what we concluded through all of this work. And if we wanted to go a step further, we could assess effect size. This is all information you've seen before. So formulas for eta squared and omega squared, you can plug in your values here. But for example, with eta squared, if we get a value of 0.21, we can say 21% of the variability in how long employees said they would stay at their company can be accounted for by the perceived stress of the workplace. Right, and then omega squared corrects for some of the limitations of eta squared. And so you can see here it's more conservative, 0.14. So our omega squared would suggest that 14% of the variability in how long employees said they would stay with their company can be accounted for by the perceived stress of the workplace. All right, so that was a lot to take in. Like I said before, if you have trouble with anything, just go very specifically, step by step, through the slides and check the values, check the notation and whatnot. Then hopefully that will lead you to the right conclusion. And if you need help, as always, just ask. All right, we'll stop there. We'll see you in the next one.